Okay. Well, thanks for the introduction. This is a presentation that I gave, so thanks for coming, everybody. I'm Joel Jansen, and for those of you who might not know me, I'm director of, I hate that title, geophysics at Lundin Mining. This is a talk, I guess it was Dennis who corralled me into giving this talk at the Saga at the Saga conference in Windhoek, and in memory of Saga, I actually wore my Saga T-shirt today. And then what was actually really kind of neat was Saga got in touch with me like 2 months ago and said, "Would you give your talk at our monthly meeting?" And I said, "When is it?" And they said, "It was this morning." So I've actually, after months of not giving it, I gave it this morning, and now I get to give it again. So I thanked them. I said, "There's the only thing better than being invited to give a talk is being invited to give a talk again, because the first time is a lot of work, and the next time is less work." So the topic is, or the subject is Semblana, and Semblana, as we'll see, is one of the I guess 7 deposits at the Neves Corvo mine in Portugal. I should start by thanking my co-authors, who are Victor Araujo, he's the geology manager at Neves, and Scott Napier, who actually, one of those two guys would be better giving this talk. They were both on the ground. Victor works there now. Scott was working in Portugal when Semblana was discovered. So Scott's real input is going to come because he contributed all the 3D EM, and he gave a talk a couple of months ago or late last year or something about 3D EM, and I think this was I think he sort of cut his teeth on this 3D model and then went to the other one. So anyway, we're on. So the acknowledgements, of course, Mira, High Size, and Bell, they both collected 3D seismic and ag data there. Mira, and Dick West, who was Lundin's director of geophysics for about a decade or so, and he was instrumental in getting a lot of these surveys off the ground. He also wrote a really good and presented a really good paper at Exploration 17. So I used a lot of that. So I call this talk Rediscovering Semblana because, well, of course, we can't rediscover something that's already been found, but a lot of things about the timing of when and how Semblana was discovered, and the data that sort of came after it. And then, so I'm going to go through the real history of the discovery of Semblana, and then if this was a blank sheet today, how would we do it? But this is a neat quote that I picked up, and this was probably in the first real paper that was written on Neves Corvo, and fine, it was written specifically about Neves Corvo, but I think it's pretty true, I think, about anything that we're going to discover these days. Right, these days, with things being covered, everything's going to be an integrated interpretation of hyperspectral geology, mapping, geochemistry, geophysics, structure, you name it. So without geophysics, Neves Corvo would not have been discovered. On the other hand, there would be no mine in Neves Corvo if the exploration had relied solely on geophysics. And yeah, I mean, it's interesting. And there's a lot of serendipity involved here. There's a lot of incorrect interpretations, but it's the hockey playoffs right now, and if you're a goalie, you have to be good to be lucky, right? So, and I think the people who have worked here over the years have been good. So a bit of an introduction, a little bit of a geological setting. We'll have a bit on the actual discovery of Neves in 1977, then discovering Semblana, and then this kind of rediscovering Semblana, and then we can wrap up and have some questions. So this was Lundin Mining last year. There's actually one more mine that didn't really fit in here called Caserones, which used to be Regalito, and then anyway, and then this was as of 8 days ago, and as of 7 days ago, it actually looks like this. So Neves and Zinkgruvan, which is another VMS, underground VMS, in Sweden, and it was actually Lundin Mining's first mine, purchased in early 2000 or so. They were sold to Boliden, and that closed late last week. So I'm actually talking about something of which I have nothing to do anymore. Zinkgruvan is an interesting one. It's been mining for like 140 years continuously, and they're still finding more and more. And it's kind of, if any of you are, in Ontario or Northern Ontario, Zinkgruvan is basically a mine in the middle of Huntsville. Like that's what it's like. It's that kind of rolling boreal forest, and it's also littered with people and it's cottage. So it's a really neat place. Neves-Corvo, on the other hand, is in the Algarve in southern Portugal, and that's a really neat place too. I'm going to miss going there. Good wine, good people. So the Neves-Corvo mine, here's a sort of a satellite image or an air photo with the 1, 2, 3, 4, 5, 6, 7 deposits there in a scale bar. So it's a VMS, volcanogenic massive sulfide, located in globally important IPBs, the Iberian Pyrite Belt. It was discovered in 1977 by drilling a gravity anomaly that was misinterpreted. Lundin got it in 2007 from Eurozinc. Before that, it was a Rio Tinto joint venture with Semincor, and now it's Boliden. And these 7 deposits, they all have published reserves. Zambojal, Semblana, Monte Branco, they're not really being mined much these days. Semblana, not all. Monte Branco, no. Has an average grade, let's say, of low 2% copper plus zinc, and then it's got some silver and lead credits to its name. So Semblana itself was discovered in 2010, and as the story will show, it's a true integrated discovery. There's obviously, it's covered, so there's no mapping, but there was a geological understanding because Zambojal and Corvo and Grassa had all been found. So we're trying to understand the stratigraphy, constrained gravity inversion, ground TEM, and then the actual discovery, the last bit was vectoring in using borehole EM, 3D borehole EM. And its resource is there. It's a bit higher grade than the rest of the deposit, and it is currently not being mined. It's 800 meters deep. You can see it's a little bit offset from the rest of the mines, and there's some other complications to go with it. But it's a neat little ore body. So a little bit on VMSs. It's a metal sulfide ore. They're mainly copper zinc. They form at depth in the submarine environments by the precipitation of hydrothermal fluids. So the first black smokers were found by NOAA, I guess, off the Galapagos in like 1973. That's when they found the first one. So that's this modern analog. I'll just that's a bit of a segue. I worked for when I worked for Teck, I was seconded to Nautilus for 2 years doing, we were calling it SMS, seafloor massive sulfide. But these things, Brunswick, Kidd Creek, Neves-Corvo, Zinkgruvan, these are all formed on the seafloor by these hydrothermal vents. So to get the fluids going, there has to be a heat source. So there's generally some sort of volcanism, fairly proximal. There probably has to be a lot of sedimentation going on at the same time. And I think in the Nautilus story, these black smokers, they're all over the place. But if these things are not covered quite quickly, the mineralization just appears into the seawater. So I think the modern ones, it's tough to find something that's being emplaced and covered. So I think that's maybe a big difference today. Anyway, there's big mining companies for the last 30 years, the BHPs, they've all been eschewing VMSs as being, they're fairly high grade, but they're too small, right? They're not small, they're not long life enough, unless you're really lucky and you find something like Kidd Creek. But I think times are changing with things getting harder to find. So there is interest in majors looking for VMSs again. And they do have these co and byproducts. So the Iberian Pyrite Belt itself, it's southwestern Spain, crosses the border into Portugal. It's about 250 kilometers long, 70 kilometers wide. Has a combined 2 billion tons of massive sulfide mineralization. It's been mined for over 5,000 years. So the Phoenicians went in there, and then the Romans, and then basically in the early, in the couple hundred AD, it all just kind of stopped. Nothing happened there for, I think, basically over 1,000 years. And then in the mid 1800s, this guy called Matheson went and he went into and started up Rio Tinto. So he was the Scottish guy, and that's where the company started at Rio Tinto. At the time, they were mining the sulfur, so they wanted the sulfur, and the way that they would get the sulfur is they would burn the pyrite. So they would mine pyrite, they would set it on fire. You can just imagine the acid rain stuff, but they would set the pyrite on fire, and they would end up with the sulfur, and they're using that. Anyway, over 90 VMSs, known VMSs in the belt. 8 are these giant classified giants, greater than 100 million tons of massive sulfide, and 6 in Spain, 2 in Portugal, Neves Corvo and Ajustel will show up on some maps as well. So the stratigraphy and understanding the stratigraphy here is quite important, and it's a big part of the story. And it's quite complicated. I have a section in the next slide, but this is the very simplistic geophysicists view of the stratigraphy. So from the bottom, there's this phyllite quartzite. It's called the PQ. That's the basement. And on top of that is this VS, volcanic, or it's often called the VSC, the volcano-sedimentary complex. There's a lower and upper, and they're separated by this thrust. And one is autochthonous, which was sort of in place, and then this alloctonous was a little bit further away. It was thrust on top, and I found this really confusing to do the ages because thrusting is supposed to be old over young, but because these things were all being thrusted and sedimented at the same time, that doesn't always happen here. But you get this. So regardless, on top of the lower VS is where most of the massive sulfide is found. There can be some stockwork below it. As it turns out, there can be stockworks into the PQ in some places, and even a few places it pokes up above. And then above the massive sulfide, you get a jasper. Anyway, you get this thrust. So if you can find this thrust, that's good, because you know that there's a chance that there's going to be massive sulfide just below it. So this is the lower stratigraphy, and I told you it was kind of complicated. Lots of, not only thrusting, but of course there's thrusting, and then there's periods of extension. So you get reverse faults and normal faults, and these things are all reactivated over time. So it's quite complicated. There's the main Neves thrust, and then here's the massive sulfide, typically sitting on top of the lower VS. But you can see here, because of thrusting things, the lower VS can be repeated. So, and this was not understood when Neves was discovered. So it's hard to find something on physical properties of the Iberian Pyrite Belt at Neves Corvo. They actually don't really collect a lot. Probably, densities, but not really much else. So this is probably the one published, not that I'm going to contribute to the published literature on this matter, but this is the one publication I found. So the densities, of the rocks in general, the younger stuff near surface, that's just typical cover rocks. The massive sulfides are going to be dense, and everything else is just kind of normal rocks, and there's substantial overlap with everything. So the massive sulfides stick out, but they can be quite deep. So we'll see. Just gravity is important, but it's not a smoking gun necessarily. The resistivities, the cover rocks are kind of conductive. The massive sulfides, of course, can be conductive or not, because lots of pyrite. And then everything else is there, and again, substantial overlap. And the magnetic susceptibilities, well, there's lots of them, but I'll show you the magnetics doesn't really play a big part. So this is what the regional geology looks like. There's these two kinds of flysch on top. As you can see, Neves is actually covered, but it is at the end of this anticline. So this is the VS that is poking out. Neves is there at the other end, just outcropping is this Algestrel. And then over here, poking out of the ground too, there's a little window of the VS poking out. It's the São Domingos. But again, Neves is substantially covered. Well, it is covered. So the regional mag, you can see this big Mechelin fault and dike, Algestrel, kind of poke. You can find that through mag. São Domingo, you can find that through mag. Neves Corvo, I don't know why someone decided to take out one little cube in the middle, but you don't find Neves Corvo using magnetics. And the regional bouguet, well, fine, just in a regional bouguet, you won't really see it either. Although if you do some sort of windowing, and this is a 20 kilometer and a 3 kilometer high pass filters, you start to see things poking out. But there's a lot of noise around here too. As it turns out, this whole gravity high is probably the anticline, and the PQ, the dense basement rock, is just getting closer to surface. But still, you window it out and you start to see some decent, some correlations between these deposits and these filtered highs. I don't think in 1977 anyone had a 20 kilometer and a 3 kilometer high pass filter that they were running on their stuff. But nevertheless, this was it. And of course, with all great discoveries, they occur on the edge of a map sheet. Neves was no different. So there was a lot of, there's a gravity collected between 1970 and 71, probably all hand contour. This is it. You see the town of Neves. There's a little high poking up here. So actually this survey was, started in 1969 on a 100-meter grid. One of 10 high priority anomalies. They thought it was less than 150 meters deep. In 1973, they drilled this hole N1. It stopped in this coulomb, which is the kind of the flysch below the VSC. So that was kind of weird because, of course, it's being thrusted, right? So there's flysch on the surface and flysch underneath. But that whole thrusting wasn't really appreciated, so they got really confused. The anomaly wasn't explained. Anyway, they stopped. They didn't fund a second hole. The bouguet density in the hole was too. So this is the problem. In their model, the bouguet density was too low. Neves was modeled at 80 meters depth, which was too shallow. They found this coulomb, where this is the Baco Alentejo flysch group. Unexpectedly encountered at the bottom of the hole, so they didn't understand the thrusting, and they missed it by 100 meters. The other thing that happened in 1973, I don't know how much you guys know about the politics of Portugal, but they had a big coup, and the government was sort of kicked out. So Portugal was in a little confused state, so everything kind of stopped. But in 1974, they got money. They did more gravity stations, so they collected the other side of the map. So they kind of closed Neves. This is the very simplistic model that they had in 1973. So just a kind of an anticline, but we really don't see any kind of the thrusting that really exists in there. So after this first hole, and while they were collecting all this other gravity, they were drilling a few holes in a few other places and doing a lot of mapping and starting to put the thrusting story and starting to understand the stratigraphy a lot better. So anyway, so this was the first model. I mean, they had discovered that there was this, excess mass. Anyway, they in 1974, with this improved geological model and structure and understanding the stratigraphy, they started to doubt this model. And they reinterpreted in 1976, and they proposed a deeper hole. They got funded, and they found this hole. So it wasn't like within 150 meters of surface. Of course, it's more like 300 meters of surface, but they intersected 53 meters of massive sulfide. So one of the first blind VMS discoveries in the Iberian Pyrite Belt. And within 2 years, and not surprisingly, they found Corvo, Grassa, and Zambuja. So I told you that there's a lot of overlap in the physical properties, and here's showing the densities by units. Yeah, so of course the massive sulfides and the stockwork will stick out, but everything else is pretty much the same. I guess when Mira does their homogeneous inversion of all the different units, issue geology doesn't have to be that correct between them. So discovering Semblana, Lundin bought Neves or it closed in 2007, and right away Lundin's always been pretty good at buying things, buying operations, and then expanding the resource. So they did that successfully at Zinkgruvan. When they did that, and at their most successful one was Candelaria when they bought it in Chile. They bought it in 2012, whatever. It had 7 years of mine life left. Now it's going to go into the 2030s. So they threw a lot of effort into understanding the geology, getting all the data together, and trying to merge it all together and make some sort of integrated interpretation. So they had their geology sections. One of the first things that they would have done was thrown it all into GoCAD, which at the time, I think, GoCAD and mining wasn't common. It's probably still not well, GoCAD isn't common today, but most companies will have someone who's running Leapfrog. But at the time, no one really did any of that. So they had these models, and of course they could kind of simplify them because some of the, as we showed in the last slide, all the units, they overlap, and they would populate this, and they did their, I don't know, I mean, how many of you know the playbook, but you run homogeneous inversions, so you might go one unit at a time. You try to come up with the best fit, what homogeneous density in each unit lowers the misfit, and you do that kind of unit by unit, and then you can start to do some geometric conversions and try to move some contacts in areas where there's a lot of inferred nature of the contact because of sparse drilling. And then in the end, and especially here, because we knew that most of the massive sulfide was associated with the VS2, the lower VS, they could run a heterogeneous version on that and then try to find the real localized density anomalies in it. So an output of that was this kind of 0.25 gram per centimeter cubed isoshell, and it overlaps quite nicely with many of these nice deposits. And then of course you go looking at field, and there's this one, and then there's these little things that come down and they go on top of Semblana. And you go, well, of course no one knew that Semblana was there, but these things are going down dip, and hey, that's kind of interesting. So what's next? So at the same time, they were blanketing the whole area, and this was being done before. They were blanketing the whole area with moving loop TEM, and Dennis was involved with collecting, some of this data. 1 by 1 kilometer fixed loops, typically 2 lines per loop, sometimes 3. You can see sort of on the edges. They're 400 meters apart. And this stuff was actually collected by Crone. Sorry, Dennis. Although you were there supervising, right?
Contract.
Yeah. Okay. So 5 hertz, 50% duty cycle, and fine. This whole area was blanketed.
With a squid.
Was this with the squid then?
Yeah, that's the reason I contracted.
Oh, that's right. This was the land. This was the land 10, right?
I wanted to see the land 10 in operation.
Yeah, yeah. Have someone else do it.
Exactly.
So this was all done. That's all kind of exciting. Makes kind of sense. We're looking for, for conductors. And then I think Scott actually did this inversion. This is a 1D inversion of the data. And it's like, hey, we got this density shell. And we've got this kind of 1D kind of, it looks kind of crude, but there's this conductor there. So that was kind of motivation. They they planned a 3 drill hole program. But it wasn't quite that simple because I didn't talk about it. But when you collect gravity over 3 decades, there's going to be screw ups in that data set, and they're all over the place, right? And the books are long gone. All the stuff at the start was typed in, transcription errors. So there's a lot of internal debate about was this density real? Right? This was deep. These densities real? Was it spurious? Yeah, I think, so I've been told there were some lively debates going on in the time. But anyway, they, 3 holes wasn't a lot, and they were looking to expand all this. So they did it. They planned a 3-hole program. And just to, I gave this at Saga, but many of you may know this, but these are just the borehole conventions. Axial is positive up the hole. U will be orthogonal to that in a vertical plane, and then D is sticking out to the side. So we're looking in this image here, we're kind of looking to the north. So the hole is kind of drilled to the south. The hole is kind of coming out of the page a bit. So we have a very weak late time anomaly here, and I'm going to cut it right. So here's our late time off hole anomaly. And, this is noisy, but there is a crossover in the U component. So going from positive to negative, this means it's to the left. So, we're looking kind of out of the page. So left means to the east. So there's something to the east. And on the V component, it's going from positive to negative. So it's behind the hole. So we should be moving east and north. And then they seem to have moved east. I don't know why they didn't really move north. I mean, it is offset a bit, but they didn't move north a lot. And now they got even a stronger off-hole response. But now they moved too far so now the U crossover is going the other way. So they should be heading to the west, and it's still behind the hole. So in this, this is what the deposit what the ore shell looks like, but the guts of the conductor are in there. And when they finally drilled, and then so now you should move back, and instead of moving back into the middle, of course, they move over like 20 meters, but whatever. They get another off-hole anomaly, but this looks like a little in-hole here, and who knows, maybe that was, the difference with this in-hole is that they actually found stuff in the hole, which is very good. So this was the discovery, this one box. This was the discovery of Semblana. And then when they found that, the floodgates were opened, and they started to drill the bejesus out of it. This is all 2007, 2008. So if we had to rediscover Semblana, it's the first thing. I think anyone suggests that you want to spend 3 decades collecting gravity data. They're kind of crazy. It's amazing. I mean, it can still be difficult to sell airborne gravity surveys. Because probably at the start these things were being marketed or as discovery things, but to me, airborne gravity is a mapping tool, right? We need density to map the geology, but this is what it looked like. This wasn't collected until 2012, but they collected the whole thing in like 2 weeks or whatever instead of years or decades. So comparing that to the coverage, again, this took years, this took weeks. And then this is something that didn't, at the time when it was flown, Bell, they didn't even they gave the components and they gave a GZZ, but they didn't give a GZ. They didn't actually do it. So when I was at Neves and floating this idea, and actually Bell asked me, they gave a short course and they asked me if I would talk. I said, I don't really have much to talk about. And then I said, hey, you guys never delivered GZ. And they said, oh, that's because we didn't do it then. Anyway, so they said, well, let us do it now. So it was kind of, for me, speaking at their little session, they did all this processing for us. So they came out with GZs, and they have this thing called source body migration. If you talk to Column, he'd be glad to tell you about it. But they basically can sort of migrate the data. I don't understand it exactly, but they come up with depth slices. They do sort of wireframing, can come up with, these aren't vectors actually, these are rasters, which is kind of weird, but that's just the way it is. And then you can sort of just color it differently, but you start to overlap things. And you show this to the geologists, and they're going, "Wow, like this is actually mapping geology at depth." And when I show this to the geologists, like in May or so, they're going, "Wow, if only we had this 15 years ago or more." So I think gravity. So AGG is one thing that you would definitely do. Of course, the other thing is seismic reflection. So this is just a kind of a stock impedance density versus velocity and curves of constant impedance. So massive sulfides stick out. We all know that, I think. But my first job ever as a geophysicist was collecting UTEM data at Neves Corvo in 1991. And these CGG people were on the ground doing seismics. So we would be doing a line, and they might be, a kilometer away, but we would see them working. And this is Lombador, which is one of the deposits probably didn't spend enough time pointing them all out. It's kind of the northern or the northeastern one. It's fairly deep, and it was a wonderful reflector. Now, not everything in Neves is a wonderful reflector, but Lombador is wonderful. So from 1991, after that, I think they went back in 1992, and no one ever did seismics there again. And I think fine, seismics is probably expensive, but I think there's a fear component. Most geologists, and certainly most mineral geophysicists at the time, didn't really understand stuff about seismics, and everyone wants to come back to what you're comfortable with, which was gravity, especially because you could, you had a job because you knew it was going to take 15 years to collect all the gravity that you needed, even in a place where you can work year round. Anyway, Lombador was visible. It took 19 years to undertake the full 3D survey. This is the Semblana cube. Now, the other interesting thing about Semblana is as soon as Neves was acquired by Lundin, Dick West wanted to do seismics, and Lundin, as a company, did 3D seismics here first, or actually probably in Ireland before that. We're looking for Irish type zinc deposits. So Lundin was one of the first, I think, bigger mining companies to go to a company like HiSeis and start to collect 3D seismic. So we got this 3D seismic cube. Dick started planning this in 2007, and basically was putting the whole story together, selling it to management. Everyone was on board. 2009, the global financial crisis hits. Then there's no money. So this didn't end up happening until 2010 or 2011, when it was planned. But in the meantime, it had been discovered. But had the seismic happened according to plan, this likely would have been a seismic discovery, or seismic would have had a big part to play, because this stands out really well. So just kind of a look into the whole seismic cube, and we're kind of looking to the northeast here, but the top of the upper VSC below that flysch really stands out. There's Lombador, and there's Semblana. Some things don't. The stockwork texture, it's like it's kind of like a breccia. Where's the good reflective surface? But when you get nice massive mineralization like you do at Semblana, you can get some nice stuff. So and then the 3D EM response. So before I was hired, Neves went and contracted me again to do a 3D EM interpretation, and Scott did it. And I guess having been the one who sort of oversaw or was on the ground when all the data was being collected. He had to understand that everything made sense. But what was interesting was when he put it all together, Semblana doesn't show up in the 3D model. The 3D model does not find Semblana. And in fact, having noticed that, he then forced Semblana into the 3D model, right? Put a block in there, gave it the right conductance. It's only like it's a 1 Siemens per meter body, so 50 meters thick, so 50 Siemens conductance. Does a forward model, and this is the different. This is it here. Like this is I don't know which is which. It doesn't really matter. But one of these is with the body, and one of it is without. And you would struggle. I think anyone would struggle to say that this migration here is maybe meaningful. So as it turns out, we don't think that Semblana is actually discovered by EM. So oh, sorry, we won't go there. So what was it? And I guess I'll just go back a few slides. I thought I had one in here. Where is it? Sorry. Just up here is Zambojao, which is shallow and near surface, and it's actually within the sphere of influence of the transmitter loop. So we now think that this 1D inversion here was just finding Zambojao that was like a kilometer away. So we'd say that you want to do 3D EM inversions. I mean, 1D EM inversions and MT. Well, for EM they're quick and dirty. Well, they're quick, but they might be quick and dirty, and I guess we have to watch out for the dirty. But there's a lot to be discovered, or that you can understand from simple models. But there's a bit of a caveat in there as well. I'd say MT is something that's never been done, but I'd just keep on about MT and all these. The beauty with MT is that at each station you can do a polar diagram and find out if the thing is. So you can do a 1D, MT anomaly, but just looking at the data, you can analyze each station independently and decide whether a 1D interpretation or how meaningful it might be. But so as part of the talk, knowing that we couldn't find Semblana. By the way, if you make it 10 times more conductive, you could find it. I asked Scott just to do a quick MT model, and it kind of has a parent resistivity model and a bit of a phase anomaly. So I was slowly trying to sell the boys on doing MT there. Of course, there's people, like I said, it's like Muskoka. There's people living everywhere. There's power lines everywhere. But for a small trial survey, especially when you can go across something like Semblana that's not being mined, and we understand a lot about it, it would have been a good test. So I hope they do that one day. And so how do we rediscover Semblana? I think at the start, everything has to be good geoscience. We don't get anywhere without that. They need good people, smart people asking good questions. You need high quality geophysical mapping, to target the physical properties, the contrast of interest. So AG, MT, or low frequency B field TEM. Now it's probably 5 hertz, is probably too high. I think our stock is now 2.5 or 1. 3D seismics. You want these geologically constrained 3D inversions, and you want people who know how to do them. Integrated interpretation. You need and this kind of preaching to the converted these days, but leapfrog geoscience analysts, you need to be putting these things in 3D. And then in the end, you have to have someone who knows how to interpret borehole EM, because you can miss these things probably by about 50 or 100 meters, and you can see them even in really noisy data like I showed you before. So here's my epilogue. John Keynes, I'd rather be vaguely right than precisely wrong. That's always true. And then I'll make George Box, all models are wrong, but some are useful. So that's it.
Thank you, Joel. Is there any questions from the audience?
On that 3D seismic cube over Semblana, the obvious bright layer, but do you know what the satellite things are on the left side there?
Yeah, I don't. These like this stuff up here is quite likely the top of this VSC. So that's the stuff above it, and then the stuff on the sides. Yeah, no, I mean if you look here, there are some. Even this hole here has two little intercepts of something, a little bit of sulfide.
I was particularly thinking about the one up and to the left.
Oh, that one there. Yeah, no, and
Being a bit shallow.
yeah, this is probably this is the problem with seismic there. I'll probably screw it up, but all reflectors are not, all sulfides are not reflectors, and all reflectors are not sulfides. So it's probably one of the bigger challenges of selling seismics again today, because when they show up really well, and when they don't. That being said, this survey took a couple of months. In fact, I think they went back twice. There was kilometers of wire on the ground, and these days with a node survey, they can come in. There's no more wires, so this survey would be done in a fraction of the time. So I would like to see them do it over Lombador. We're doing a lot of exploration around Lombador, so I was sort of trying to pitch that, but it won't happen, at least not with me. Yes?
Do you think if you did the moving loop EM at a lower frequency, it might help you find it, or do you think it's not findable with the EM?
I think, is Scott online? I think Scott actually dropped the frequency of the thing, and I think here at Semblana it doesn't really, like, going from 5 hertz to 2.5 hertz isn't enough really to throw it over the top, because there are it's basically because the host with all the shales and the flysch are just so conductive. So here, I don't think that would make a difference, which is why I was saying, look, I think you need to go really low frequency, so for the MT, but that would be a processing challenge to try to get signal out of the noise.
Speaking of the future, do you have any idea of what Leeden's going to be doing? Are they going to expand their regional program, or are they going to just focus on the ore bodies and try to mine them out? Or
I have no idea. I mean, from the business perspective, I think Boliden, from what I've heard, was really the only logical purchaser of it, because they're a vertically integrated company. So they bought Neves Corvo to feed their smelters, to guarantee them feed. So, there is work going on at Lombador North right now. That's the focus around Lombador, the northern end of Lombador. So there is stuff going on, but whether they're going to go and do more in around Semblana, who knows? Yeah. I mean, it's amazing that Boliden has never owned Zinkgruvan.
Yeah.
Yeah. Just because it's in Sweden and it's big.
Joel, I was curious what your comment with the 1D inversion result potentially being an updip conductor. Did you or Scott model that and sort of see if that would actually fit the data, or is that just a working hypothesis at this stage?
Yeah, actually, I don't know if Scott actually went and modeled that. The only thing we know is that when he does the 3D inversion, the 3D inversion finds some stuff really, really well. It doesn't find anything here, right? And certainly when you like showed you when you did the forward model, basically came back and looked just like the data, right? So there's no, I mean, you can't invert Semblana out of that, right? Find a thing at 800 meters deep because of this little migrating crossover. So yeah, you're right. I mean, maybe we're poking at it a bit too far. There's definitely, the 1D inversion is showing that there's definitely something conductive under there, and but yeah, it may be a bit of a, that's the most plausible thing that we have, because Zumbergeld is a lot shallower. It's only like 100 meters deep or so, and it is clearly within the sphere of influence of the transmitters. It's our working hypothesis. Until someone refutes it, we will.
And 50 seconds is not a lot.
Yeah, no, these things are not, because they're mostly pyrite. They're not, you think massive sulfide, and maybe you start to think, something in Sudbury, you got like 5 meters of pentlandite, and you get 1 million Siemens. No, this is not like that.
Any questions online? I haven't seen any, but
What do I find out if they're?
I haven't seen it.
No. Okay.
Otherwise, wonderful. Thank you, Joel.
Thank you.
I would encourage a group to go for a beer after. It's the new